You are sitting in a room that feels stable. The air has weight. The floor resists your feet. Light reaches your eyes from objects you assume are where they appear to be. You believe that if something exists somewhere in the universe, information about it could, in principle, reach you given enough time. This belief is not philosophical. It is built into how you understand distance, causality, and the meaning of observation. But there are regions of the universe that violate this assumption without violating any known physical law. Regions whose existence is not inferred indirectly, but measured. Regions that do not merely hide information, but permanently prevent it from ever arriving, no matter how long you wait. The boundary that defines these regions does not behave like a wall or a surface. It behaves like a limit built into space-time itself. This boundary is called an event horizon, and once it exists, reality becomes divided into what can still influence you and what never will, even though both continue to exist under the same physical laws. The question is not what lies beyond it. The question is what it means that such a boundary can exist at all. The assumption of universal visibility. You begin with the intuitive belief that space is a continuous expanse where distance is only a matter of time and speed. If something emits light or any signal, you expect that signal to propagate outward indefinitely unless blocked by matter. This assumption holds in everyday experience and even across most of astronomy. Yet observations already show that this intuition fails at large scales, where visibility is not limited by obstacles, but by the structure of space-time itself. This belief is reinforced by how measurement has always worked for you. When you look farther away, you look further back in time. A star 100 light-years away appears as it was 100 years ago, but you assume that patience resolves the gap. Wait long enough, and information arrives. Distance delays, but it does not exclude. The universe, in this picture, is slow, but ultimately accessible. For centuries, astronomy seemed to confirm this. Larger telescopes revealed fainter galaxies. Longer exposures pulled structure out of darkness. Every improvement in instrumentation extended the observable frontier. Nothing suggested a fundamental limit. The night sky appeared finite only because of technological constraints, not because reality itself imposed boundaries. But modern cosmological measurements undermine this assumption quietly, without spectacle. When you measure the redshift of distant galaxies, you are not just measuring how far away they are. You are measuring how the space between you and them has changed while the light was in transit. These measurements show that space itself is expanding. More precisely, the distance between distant regions increases even when neither region is moving through space in the conventional sense. At first, this expansion seems compatible with universal visibility. If space stretches, light still moves through it. Given enough time, signals should still arrive. But further observation reveals a critical detail. The rate of expansion is not constant across all scales. Beyond a certain distance, the expansion of space outpaces the ability of light to cross it. This is not a failure of light. Light continues to move locally at its measured speed. It is not absorbed or scattered. Instead, the space it must traverse grows faster than the light can progress. The destination recedes not because it moves away, but because the metric defining distance itself changes while the signal is en route. This creates a situation your intuition is not equipped to handle. There are objects whose light is already reaching you, but whose future light never will. You can observe their past, but not their future. The signal you receive today is the last one you will ever get. even though the object continues to exist and emit radiation. Here, visibility ceases to be a question of time. No amount of waiting brings the signal. No improvement in sensitivity recovers it. The absence is not due to obstruction or decay. It is enforced by the geometry of space-time. This forces a revision of what you mean by accessible reality. You are accustomed to thinking that existence implies potential observation. Cosmology shows that this link is contingent. There are regions that are real, dynamic, and governed by the same physical laws as your own environment, yet permanently excluded from causal contact with you. Importantly, nothing dramatic marks the transition. There is no edge you can point to in the sky. No visible boundary separates what will remain observable from what will not. The distinction emerges only when you account for the full future behavior of space-time. Visibility becomes a global property, not a local one. This undermines the assumption that the universe is observationally unified. Even in principle, you cannot assemble a complete picture. Your measurements are not merely incomplete due to practical limitations. They are incomplete because the structure of space-time guarantees permanent exclusion. At this point, the event horizon is not yet a physical object. It is an implication, a consequence of accepting the data as measured. If space can expand in this way, then visibility is conditional. And if visibility is conditional, then the universe is already partitioned into regions that can influence you and regions that cannot, without violating any known law of physics. The assumption of universal visibility fails not because the universe is hostile to observation, but because observation itself is constrained by geometry. This is the quiet beginning of the horizon problem. When distance becomes a deadline, you are accustomed to thinking of distance as passive, something that can always be crossed eventually. But cosmological measurements show that the universe is expanding and not uniformly. Beyond a certain scale, space itself stretches faster than light can traverse it. This introduces a deadline rather than a barrier. Past a specific distance, signals are not delayed. They are prevented from ever arriving. This distinction matters because it reverses how you interpret separation. A barrier implies resistance. A wall blocks, a cloud obscures, a medium absorbs. In each case, greater energy or improved technology promises a solution. A deadline offers no such option. Once it passes, no future action alters the outcome. The signal is not slowed. It is excluded from your future light cone. The evidence for this comes from consistent measurements of cosmic expansion. When you observe distant galaxies, their light is stretched to longer wavelengths in a way that correlates precisely with distance. This redshift is not random. It follows a pattern that reveals how fast space has expanded during the light's journey. From this pattern, you infer not only that expansion is occurring, but that it accelerates over time. Acceleration changes the meaning of reachability. In a universe expanding at a constant rate, distant signals might arrive eventually. In an accelerating universe, some distances become unreachable no matter how early the signal is emitted. The expansion compounds faster than the signal's progress. Space adds new distance faster than light subtracts it. You can visualize this not as motion through space, but as the stretching of the grid that defines distance itself. Each moment, the grid expands. A photon moves across the grid at a fixed local rate, but the grid grows beneath it. Beyond a certain scale, the growth outpaces the crossing. The photon continues to move, yet never closes the gap. This scale is not arbitrary. It can be calculated from observed expansion rates. It defines a radius around you beyond which future communication is impossible. Objects beyond this radius are not hidden. They are causally disconnected from your future. Their signals belong to a past that is already complete. This creates a subtle asymmetry in time. You may currently observe a galaxy that is already beyond this deadline, the light reaching you left long before the expansion crossed the threshold. What you see is a record, not a relationship. There is no ongoing exchange. You are observing a history that has no future continuation. From your perspective, nothing marks the moment communication ends. The galaxy does not fade abruptly. It does not blink out. The transition occurs in space-time, not on your detector. One emission arrives, the next never will. The cutoff is invisible because it is not local. This challenges the assumption that causality fades gradually with distance. Instead, it ends sharply, but along a boundary defined by cosmic dynamics rather than material limits. The universe enforces a horizon, not by obstruction, but by timing. Once this deadline exists, the universe becomes stratified by causal access. There are regions whose future evolution can influence you, regions whose past can influence you, but whose future cannot, and regions that are entirely disconnected in both directions. These distinctions are not philosophical. They are consequences of measured expansion parameters. You are not located at a privileged center. Every observer carries their own version of this deadline, centered on their position. The horizon is not a fixed structure in space. It is a relational feature between observers and the global behavior of space-time. The unsettling implication is not that information is lost, but that relevance is constrained. Events continue to unfold beyond your deadline. Structures form, stars evolve, entropy increases. None of it is accessible to you, not because the universe is finite, but because time itself has become a limiting factor on connection. Distance has stopped being a question of how far. It has become a question of when. And once the answer is too late, the separation is permanent. Segment 3. Horizons without walls. An event horizon does not mark a place where physics changes locally. If you were near one, nothing in your immediate environment would announce its presence. No force would push you back. No surface would resist you. Yet despite this local normality, global consequences emerge. Paths that once connected events are no longer possible, even though nothing obstructs them. This absence of a local signal is central to why horizons are difficult to accept intuitively. In most physical situations, limits announce themselves through interaction. A boundary exerts pressure. A field produces a force. A medium alters motion. An event horizon does none of these things. It is not an object you encounter. It is a condition imposed on the future structure of space-time. To understand this, you have to separate what happens at a point from what happens to all possible paths extending from that point. Locally, physics remains unchanged. Clocks tick normally. Light behaves as expected. Measurements performed in a small region reveal no anomaly. Yet when you extend those measurements forward in time, their outcomes diverge depending on whether a horizon exists. The horizon reveals itself only when you consider trajectories rather than locations. A trajectory is a complete path through space-time, not just a position at a moment. The event horizon divides trajectories into two categories: those that can still reach distant observers and those that cannot. The division is absolute. Even though the local laws governing motion are identical on both sides, this creates a boundary that is not spatial but causal. It does not separate places. It separates futures. two events arbitrarily close in space can have fundamentally different causal outcomes depending on which side of the horizon they lie. One can influence the outside universe indefinitely. The other cannot influence it at all. Because nothing changes locally, the horizon cannot be detected by crossing it. There is no moment of impact. No marker in the equations of motion announces the transition. Only when you reconstruct the full causal structure do you discover that something irreversible has occurred. This irreversibility is not due to dissipation or entropy increase. It is geometric. Once a horizon forms, the set of all possible future connections is permanently reduced. Paths that existed in the mathematical description before no longer exist afterward. The loss is not gradual, it is structural. This property forces you to rethink what a boundary is. A wall blocks motion through force. A horizon blocks influence through geometry. Nothing prevents motion locally. What disappears is the possibility that motion leads anywhere externally meaningful. This also explains why horizons depend on the entire future of the universe. Whether a signal escapes cannot be determined by local conditions alone. It depends on how space-time evolves indefinitely. The horizon is defined not by where you are, but by what will never happen. This undermines the idea that boundaries must be observable or localizable. The horizon exists even though no measurement at the boundary reveals it. It is a global feature inferred from consistency, not detected directly. Once this is accepted, the concept of isolation changes. Isolation no longer requires distance or obstruction. It requires only a divergence in causal structure. Two regions can remain adjacent and yet be permanently disconnected in influence. This challenges the assumption that continuity guarantees connection. Space-time can be smooth and uninterrupted while still partitioning reality into regions that cannot communicate. The universe does not need to tear itself apart to isolate its components. It does so by redirecting futures. At this point, the event horizon is no longer an exotic artifact of extreme objects. It is a general consequence of how space-time can be arranged. A boundary without walls, a division without force, a separation that leaves everything locally unchanged while quietly altering what can ever matter. Segment 4. The black hole as a measured object. Black holes are not theoretical curiosities. Their masses are measured through orbital dynamics. Their presence is confirmed through gravitational waves. Their shadows have been imaged. Within these objects, event horizons form naturally from solutions to Einstein's equations. These horizons are not assumptions. They are required to explain what is already observed. You do not infer black holes because you want them to exist. You infer them because alternative explanations fail under measurement. When stars orbit an unseen center at extreme speeds without dispersing, the mass required is too compact to be anything else. When space-time itself ripples in patterns predicted decades in advance, the source must be objects dense enough to merge without leaving material debris. These are not interpretive choices. They are constraints imposed by data. The role of the event horizon in this picture is not decorative. It is structural. Without a horizon, the equations describing gravity under extreme compression produce contradictions. Matter would have to behave in ways already ruled out by observation. Energy would need to escape from regions where no known mechanism allows it. The horizon is not added to protect the theory. It emerges because the theory otherwise breaks. You might expect something so consequential to announce itself violently. But again, the horizon is quiet. It does not generate radiation on its own. It does not exert an extra force. Its presence is inferred because nothing escapes, not because something unusual happens at the boundary. The absence of outgoing information is the signal. This absence is measurable. In binary systems where one object is a black hole, matter drawn toward it heats and emits radiation until it disappears. The radiation ends abruptly, not gradually. The cutoff matches predictions of infall toward a horizon rather than collision with a surface. There is no rebound, no accumulation, no delayed emission suggesting impact. The simplest explanation consistent with all observations is that there is no surface to strike. Gravitational wave detections reinforce this conclusion. The final moments of black hole mergers produce signals that decay in precise ways. These patterns, known as ringdowns, depend on the existence of a horizon. Without one, additional echoes or reflections would appear in the signal. They do not. The silence after the merger is as informative as the signal itself. When the shadow of a black hole is imaged, you are not seeing the horizon directly. You are seeing the effect it has on nearby light paths. Photons that pass too close are captured. Others are bent around the object. The resulting deficit forms a dark region whose size matches predictions for a horizon-defined boundary. Again, the measurement aligns with geometry, not material obstruction. What is critical here is that all of these observations converge on the same conclusion using independent methods. Orbital motion, radiation dynamics, gravitational waves, and lensing all require horizons to exist as described. Remove the horizon, and each line of evidence demands increasingly contrived alternatives that conflict with other measurements. You are not being asked to imagine an exotic object. You are being asked to accept the most conservative interpretation of the data. In this case, the conservative interpretation is that regions exist from which no signal can escape, not because of unknown forces, but because space-time itself allows such regions. This anchors the event horizon in reality rather than speculation. It is not a metaphor for ignorance. It is not a placeholder for future physics. It is a feature demanded by the same equations that accurately describe planetary motion, time dilation, and gravitational waves. Once this is acknowledged, the implications extend beyond black holes themselves. If horizons can form through gravitational collapse, then the universe permits absolute causal disconnection as a natural outcome of known processes. Isolation is not an anomaly, it is a solution. At this point, the horizon is no longer an abstract boundary discussed in thought experiments. It is part of the measured universe, and its existence forces a reconsideration of what it means for something to be observable, influential, or even relevant within physical reality. Escape velocity becomes geometry. You may have learned that black holes trap light because their gravity is too strong, but this explanation is incomplete. The deeper reason is geometric. Inside a certain radius, all possible paths through space-time lead inward, just as all future moments lead forward in time. Escape does not fail because of insufficient energy. It fails because outward directions no longer exist. The idea of escape velocity comes from Newtonian intuition. To leave a planet, you must move fast enough to overcome gravitational pull. More speed offers more freedom. In that framework, light fails to escape a black hole because even the maximum possible speed is not enough. But this picture treats gravity as a force acting within fixed space and time. General relativity replaces that picture entirely. In Einstein's description, gravity is not a force pulling objects inward. It is a curvature of space-time that shapes how objects move when they follow the straightest possible paths. These paths, called geodesics, define what motion means when no forces act locally. Light follows these paths not because it is compelled, but because there is no alternative. Outside a black hole, space-time is curved, but still permissive. Geodesics can point inward, outward, or around the mass. Multiple futures remain accessible. But as you approach a critical radius, the curvature deepens. The structure of space-time begins to tilt in a specific way. Paths that once led outward become steeper. Eventually, they vanish. At the event horizon, this process completes. The distinction between space and time reorganizes. What you previously called inward becomes as unavoidable as the passage of time itself. Just as you cannot choose a future moment in the past, you cannot choose a path that increases your distance from the center. The geometry has removed that option. This is why energy becomes irrelevant. No amount of thrust changes the available paths. Acceleration alters your motion relative to nearby observers. But it cannot create a direction that space-time no longer supports. The failure of escape is not dynamic, it is structural. Light illustrates this most clearly. Light always travels along paths where time stands still in its own frame. If even these paths point inward, then nothing remains that could carry information outward. The event horizon is defined precisely by this condition. It is the surface where all future-directed light paths fail to increase radial distance. This redefinition is unsettling because it reframes inevitability. In everyday life, inevitability comes from constraint or exhaustion. In a black hole, inevitability comes from geometry. The universe does not push you inward. It simply stops offering alternatives. Importantly, this transformation happens smoothly. There is no singular moment where geometry breaks. As you cross the horizon, the equations governing space-time remain well-behaved. Curvature may be extreme, but it is finite. Nothing locally signals the loss of outward paths. The change is only visible when you consider the full set of possibilities that no longer exist. This challenges how you think about freedom of motion. You normally assume that if no force acts, motion remains unconstrained. Here, the absence of force does not imply freedom. The structure of space-time itself determines what futures are allowed. Once escape velocity is replaced by geometry, the event horizon becomes inevitable wherever sufficient mass is compressed. It is not a special case requiring exotic conditions. It is the natural outcome of concentrating energy beyond a calculable threshold. This understanding also removes any notion of resistance at the boundary. There is nothing to struggle against. No battle is lost at the horizon. The concept of losing is misplaced. What happens instead is a quiet redefinition of what movement means. By the time escape velocity becomes geometry, the event horizon is no longer a dramatic edge. It is a statement about the shape of possibility. Beyond it, the universe does not trap you. It simply stops offering a way back. Light that moves, normally and still fails. At the event horizon, light behaves locally as it always does. It travels at its usual speed. It follows the same physical laws. Yet globally, it never reaches distant observers. This is not because light slows down or loses strength. It is because the structure of space-time redirects all future trajectories away from the outside universe. This is one of the most difficult aspects of an event horizon to internalize because it contradicts how you understand failure. When something fails to arrive, you expect a cause you can point to: friction, absorption, interference, decay. Here, none of these apply. The photon is not impeded. It is not damaged. It is not altered. It simply never arrives. From the photon's local perspective, nothing unusual occurs. If you could ride alongside it, measuring its behavior in a small region, every experiment would return familiar results. The speed of light remains constant. The equations governing electromagnetism remain intact. There is no local slowdown, no loss of energy in the usual sense. The failure appears only when you step back and consider the full space-time path the photon attempts to follow. Light does not move through space alone. It moves through space-time, where space and time are interwoven. The path light follows is determined not by force, but by the geometry of that combined structure. Near an event horizon, this geometry changes how future directions are arranged. What counts as moving forward in time begins to align with moving inward in space. Light continues to move forward in time because it cannot do otherwise. As a result, it also moves inward, regardless of its initial direction. This is why the horizon cannot be described as a place where light turns around or slows. Nothing deflects the photon at the boundary. Instead, the boundary marks the point beyond which all future directed paths fail to increase distance from the center. The option to move outward ceases to exist as a future possibility. You might imagine light emitted just above the horizon, aimed directly outward. For a while, it appears to climb away. Its wavelength stretches. Its energy decreases relative to distant observers. The climb becomes slower and slower. From far away, the light seems to freeze, red-shifting toward invisibility. But this apparent freezing is not what the photon experiences. It continues uninterrupted. The delay is not in the emission. It is in the structure of the space-time it traverses. The crucial point is that global outcomes cannot be inferred from local behavior. Light can obey every local law perfectly and still fail to connect events. This breaks an implicit assumption you carry about causality, that if something behaves normally at every step, it should reach its destination. Event horizons demonstrate that causality depends not only on local rules, but on the global arrangement of space-time. The same laws applied everywhere can produce regions where outcomes diverge absolutely. This distinction matters because it means horizons do not require exotic physics. No new forces act on light. No breakdown of known laws occurs. The failure of escape is not a signal of incomplete theory. It is a prediction of the theory working exactly as designed. This also explains why horizons are unavoidable once certain conditions are met. If mass energy curves space-time sufficiently, the redirection of future paths follows automatically. You do not need to invoke additional mechanisms to trap light. The geometry does the work. For observers far away, the consequences appear paradoxical. Light seems to asymptotically approach the horizon without crossing it. Signals appear to fade rather than disappear. But this perception reflects the observer's coordinate system, not the underlying reality. From the perspective of space-time itself, the crossing occurs without hesitation. The result is a situation where light is neither stopped nor altered, yet its influence is eliminated. Information is not destroyed at the horizon. It is removed from causal circulation. Once you accept this, the horizon becomes something more precise than a boundary of darkness. It is a boundary of relevance. Beyond it, events still occur, light still moves, and physics continues unchanged. But none of it can ever contribute to what happens elsewhere. Light moves normally, and still it fails. Time tilts inward. Outside the horizon, you experience time as a progression where multiple futures remain possible. Inside, time itself points toward the center. This is not metaphorical. Mathematical descriptions show that what you call future inevitably corresponds to decreasing radius. The event horizon marks the point where temporal freedom collapses into inevitability. In everyday experience, time feels neutral with respect to direction in space. Tomorrow does not force you north or south. The future arrives regardless of where you go. Space offers choices. Time advances independently. This separation is so ingrained that you rarely question it. Yet near an event horizon, this separation dissolves. In general relativity, time and space are not fixed backgrounds. They are dimensions of a single structure whose orientation can change. Outside a black hole, this structure resembles what you expect. Time flows forward. Space extends outward in multiple directions. You can choose paths that lead away or toward the center. The future does not constrain your location. As you approach the horizon, this balance shifts. The geometry of space-time gradually reorients what counts as forward. The equations show that the role of radial distance and the role of time begin to exchange characteristics. The closer you are, the more tightly your future aligns with inward motion. At the horizon, the exchange becomes complete. Inside, decreasing radius is no longer a spatial option among others. It is the temporal direction. To move forward in time is to move inward. Remaining at the same radius would require halting the passage of time, which is not physically meaningful. This is why inevitability takes on a new form. You are not compelled inward by force. You are carried inward by time. Resisting would require stepping into your own past. The idea of holding position loses meaning because position itself becomes subordinate to temporal flow. This reframing dissolves common misunderstandings about falling into a black hole. There is no moment where gravity suddenly overwhelms you. There is no last chance seized or missed. The future simply narrows. Possibility contracts until only one trajectory remains. Importantly, this does not imply chaos or breakdown. The equations remain precise. Cause still precedes effect. Local physics continues to function. What changes is the structure of what outcomes are available. Freedom of direction disappears without violating any law. From your perspective inside the horizon, the center is not a place you rush toward. It is a time you are approaching. Just as tomorrow approaches regardless of your actions, the central singularity lies ahead in your future. Distance becomes duration. This has unsettling implications for how you think about determinism. Outside the horizon, the future contains branches. Choices alter paths. Inside, the branching ends. The future is fixed not because of fate, but because geometry allows no alternatives. This also clarifies why the horizon is irreversible. Once time tilts inward, there is no path that leads back out, because there is no future-directed route that increases radius. Reversal would require reversing time itself. The horizon is not a one-way door in space. It is a one-way condition of time. The transition is not marked by sensation. You do not feel time rotate. Your clocks continue to tick normally. Locally, nothing announces that your future has collapsed into a single outcome. The loss of freedom is global, not experiential. This distinction matters because it prevents easy metaphors. The horizon is not a trap, a pit, or a funnel. It is a redefinition of what forward means. The universe does not take options away by force. It removes them by rearranging time. Once you accept this, the event horizon becomes more than a boundary of communication. It becomes a boundary of possibility. Outside, the future is open. Inside, it is prescribed. The same physical laws operate in both regions, yet the meaning of choice changes completely. The unsettling realization is that inevitability does not require violence, collapse, or instability. It can arise quietly as a consequence of geometry. Time does not stop at the horizon. It simply stops allowing you to go anywhere else. Information that still exists. Nothing crossing an event horizon is destroyed at that moment. Matter, radiation, and structure continue to exist according to the same local laws. Yet their ability to affect anything outside the horizon is permanently removed. Existence and influence separate. Something can be fully real and still causally disconnected from the rest of the universe. This separation is subtle because it contradicts how you usually equate existence with effect. In everyday experience, to exist is to be capable of interacting. Objects push, emit, reflect, absorb. Even distant things announce themselves eventually through some chain of influence. An event horizon breaks this association without erasing the object itself. When matter crosses the horizon, no physical principle requires it to disintegrate. Its internal interactions continue. Particles collide. Fields evolve. Time progresses locally, as it always has. From the perspective of that matter, nothing fundamental has ended. What ends is its participation in the external causal network. This distinction matters because physics is built on interactions. Measurements are interactions. Observations are interactions. If something cannot interact, it cannot be measured. But lack of measurement does not imply non-existence. It implies exclusion. The horizon enforces this exclusion absolutely. No signal emitted after crossing can reach outside observers. Not now, not later, not in infinite time. This is not a technological limitation. It is a structural one. The future light cone of any event inside the horizon lies entirely within the horizon. This creates a category of information that still exists but cannot propagate. The state of matter inside continues to evolve, but its evolution cannot be reflected in any external measurement. The universe outside the horizon cannot be updated about what happens inside. The internal history becomes private. This privacy is not reciprocal. Information from outside can still enter. External events can influence the interior. But once information crosses inward, the exchange becomes one-sided. Causality remains intact, but symmetry is lost. This asymmetry forces a re-examination of what information means in physics. Information is often treated as something that can, in principle, be recovered. Here, recovery is impossible. The information is not destroyed in the sense of being erased from reality. It is destroyed in the sense of being removed from accessibility. This is why event horizons lead directly to questions about information conservation. If information exists but cannot influence anything measurable, does it still count in physical accounting? If it contributes to entropy, energy, or state counting, how is that contribution registered outside? Observations suggest that the horizon itself carries information. The properties of the black hole, its mass, charge, and rotation, change in response to what falls in. The details are compressed into a minimal external description. Many internal distinctions become invisible. Different internal states can correspond to the same external parameters. This compression does not imply annihilation. It implies loss of resolution. The universe outside the horizon no longer distinguishes between many possible internal configurations. The richness of internal structure persists, but it has no external signature. This challenges a deep assumption that reality is fully describable by what can be observed. Event horizons demonstrate that this assumption is false. There are physically real states that never enter any observation, not because they are hidden temporarily, but because they are excluded permanently. This has implications beyond black holes. It suggests that the universe can generate regions whose internal complexity is irrelevant to the rest of reality, not negligible, irrelevant. Events can occur that make no difference anywhere else. This does not make those events meaningless. Meaning is not a physical category, but it does mean that influence is not guaranteed by existence. The universe allows for fully lawful, fully real processes that leave no trace beyond their own region. Once existence and influence separate, completeness becomes questionable. You may describe everything that can ever affect you and still be describing only a fraction of what exists. The remainder is not hypothetical. It is causally isolated. The event horizon is therefore not just a boundary of observation. It is a boundary of participation. Beyond it, reality continues, but without consequences for anything else. The unsettling implication is not that information disappears, but that the universe permits information to exist without ever mattering again. Observation. Without access astronomy relies on the assumption that light carries information from distant objects to your instruments. Event horizons break this chain. They create regions whose internal states can no longer be updated in any observation you perform. This is not a limitation of technology. It is a fundamental constraint on what observation means. In every other context, observational failure invites improvement. You build larger mirrors. You observe longer. You correct for noise. The history of astronomy is a record of overcoming distance by refinement. Each barrier appeared provisional. Event horizons are different. They are not overcome by better instruments because they are not obstacles to detection. They are absences of causal connection. When you observe an object, you are not seeing the object itself. You are receiving a signal emitted earlier. The assumption is that the stream of such signals continues. Each new photon updates your picture. Event horizons terminate that stream. After a certain point, no further updates occur. The object remains, but your knowledge of it freezes permanently. This freeze is absolute. It does not depend on signal strength or wavelength. No electromagnetic radiation escapes. No gravitational influence propagates outward beyond what is already encoded. The region's internal evolution becomes observationally static. This introduces a profound asymmetry between existence and knowledge. You can know that a region exists and yet be unable to learn anything new about it. The horizon enforces a permanent observational blind spot. This blind spot cannot be narrowed. It does not shrink with time. Waiting does not help. The information you have is all the information you will ever get. The region's future is erased from your observational record, even though it unfolds according to the same laws as everything else. This forces a revision of how you interpret astronomical data. Normally, absence of change suggests stability. Here, absence of change can indicate exclusion. A lack of new information does not mean nothing is happening. It means nothing can reach you. This distinction matters because astronomy often infers unseen processes from indirect effects. With horizons, indirect inference reaches a limit. Once all external effects are accounted for, the internal details become unconstrained. Multiple internal histories are compatible with the same external observations. This undermines the idea that the universe is fully inferable from outside. You may know the mass, spin, and charge of a black hole with great precision, yet you cannot know what happens to the matter inside. The internal state space becomes observationally inaccessible. This is not a gap to be filled by future theory. It is a property of the causal structure. No theory that respects the horizon can restore access without contradicting established measurements. The limitation is not epistemic in the usual sense. It is ontological. The horizon transforms observation from a process of accumulation into a process with a terminal point. Beyond that point, knowledge stops growing while reality continues to change. The universe decouples observation from evolution. This decoupling has implications for scientific explanation. You can explain the formation of a horizon. You can predict its external effects, but you cannot track the full state of the system indefinitely. Completeness becomes unattainable by design. The discomfort arises because science relies on the assumption that observation, even if difficult, remains possible in principle. Horizons violate this principle without violating any law. They enforce ignorance not by obscurity, but by structure. This forces you to accept a universe where some processes are not just unknown, but unknowable. Not hidden, not encrypted, excluded. The event horizon does not block your view. It defines what a view can be. Beyond it, observation is no longer a relationship between observer and object. It is a memory of a relationship that has already ended. The horizon is not a place. You may picture an event horizon as a surface in space, but it is more accurately a boundary in space-time. Its location depends on the entire future of the universe, not just the present moment. Whether a horizon exists can only be defined by what will never reach you, even in infinite time. This distinction undermines the intuition that a boundary is something local and tangible. In daily experience, limits occupy space. A wall separates rooms. A cliff ends a path. Even in astronomy, you tend to imagine a surface marking the edge of an object. The event horizon behaves differently. It is not where you stand or what you touch. It is a statement about connectivity. A global condition describing all possible interactions between regions of space-time. The horizon's definition requires knowledge that transcends the present. To know whether a photon or a particle is trapped by a black hole, you must know the ultimate fate of its trajectory. You cannot determine this from local measurements alone. You must consider the future curvature of space-time and the entirety of gravitational interactions that might influence that path. Only then can you say definitively whether it will ever escape. This has profound consequences for how you understand causality. Typically, cause and effect are local. An event propagates outward at finite speed. Effects appear nearby first, then extend. Horizons, by contrast, force you to think in reverse. You determine the existence of a boundary by asking which effects will never occur. The horizon is defined not by action, but by absence of possible future outcomes. Because of this, the horizon is inherently non-local. Two observers at different positions or in different states of motion will assign different boundaries. Each horizon is relative, tied to the causal perspective of its observer. There is no universal, fixed surface marking the end of influence. The boundary exists in relation to what can be affected and what cannot, rather than as a physical object with fixed coordinates. This also clarifies why the horizon does not produce local signals. No matter where you place instruments near it, they reveal no sudden forces or anomalies marking its presence. Nothing in your immediate environment changes. It is not a material limit. It is a structural limit encoded in the pattern of possible connections through space-time. The horizon is silent, invisible, yet absolute in its consequences. In a sense, the horizon is defined by negative knowledge. It is the set of events that will never communicate with you. It is the complement of accessibility. This means that the horizon is entwined with the unfolding of the entire universe. Changes in distant regions, far beyond any direct interaction, could in principle shift the precise shape of your causal boundary. It is not static in a geometric sense. It is fixed only relative to the observer's accessible future. The implications for observation are unsettling. You might see a black hole as a dark circle against a luminous backdrop, but that circle is a mere representation. The true horizon is a condition that no photon can reveal in isolation. What appears as a surface is an emergent shadow of an invisible causal limit. Reality is more than what is captured in the image. The horizon is embedded in the rules governing information propagation rather than in space itself. Because the horizon is a feature of space-time, it applies not only to black holes, but also to the expanding universe. The cosmological horizon surrounding you arises from the accelerated expansion of space. It is determined by what light will never reach you from distant galaxies. Like black hole horizons, it is not a location you can point to, but a future-based constraint on possible observation and interaction. In this sense, the horizon is a boundary without a wall, a limit that exists because of the interplay of geometry, time, and causality. It is a statement about the structure of reality itself. Some regions are permanently beyond influence, not through obstruction, but because the universe has already arranged the future to prevent connection. It is the quietest of limits, absolute and unavoidable, yet nowhere physically marked. The event horizon is not a place. It is a pattern, a condition, a future-defined division in reality that no object, no light, and no force can alter. Understanding it requires abandoning intuition about space as a container and accepting that connectivity, not position, defines the true limits of what exists for you. Horizons and the expanding universe. Black holes are not the only structures with event horizons. The accelerating expansion of the universe creates a cosmological horizon around you. There are galaxies already visible whose future light emissions will never arrive. Their past remains observable. Their future is causally erased. In everyday terms, you think of space as infinite, or at least as fully accessible given enough time. Light travels, information propagates, and the only limits are practical. The cosmological horizon challenges this intuition. It is not a wall or a physical barrier. It is a region of space-time whose expansion ensures that the signals those galaxies emit from now on will never reach you, no matter how long you wait. Observations confirm this in measurable ways. Redshifted galaxies at extreme distances show a pattern consistent with accelerated expansion. The wavelengths of their light stretch in proportion to their recession velocity. Calculations reveal that for some galaxies, the space between you and them grows faster than light can bridge. The expansion does not slow, it outpaces information itself. Future emissions from these galaxies are destined never to enter your observable universe. This creates a stark temporal asymmetry. You are observing their history, but not their future. Every photon you detect today left them long ago. Each image is a window into a past that continues to unfold in ways you cannot measure. The universe outside your horizon is real and evolving, yet permanently inaccessible in terms of direct observation. Causality is partial, influence is truncated. Unlike a black hole, the cosmological horizon is not centered on a massive object. It is centered on you, as any observer would find themselves surrounded by their own horizon. Every point in the universe experiences its own boundary of causal connection, shaped by the metric expansion of space. This relativity of horizons illustrates that accessibility is observer-dependent, not absolute. The limits are defined by the future potential to receive information, not by mass or density. Even so, the consequences are profound. For galaxies near this horizon, light emitted today travels only so far before space stretches it away faster than it can progress. Their structure continues to evolve. Stars form, die, and collapse. Supernovae detonate. Black holes merge. These events have no chance of being observed by you. Existence and influence separate on a cosmic scale. Reality persists, yet it is irrelevant to your causal domain. The horizon also reframes your understanding of the universe's age and size. You may see galaxies as they were billions of years ago. Their light has traveled across expanding space to reach you, but the moment of observation is disconnected from their ongoing evolution. The apparent size of the universe, as defined by the reach of light, is shrinking in a relative sense, not because space contracts, but because expansion stretches distances beyond the speed of causal contact. This has implications for interpretation. Cosmic microwave background radiation, the distribution of galaxies, and measurements of large-scale structure must all be understood in the context of horizons. Portions of the universe that contribute to local gravitational effects may remain forever causally disconnected from one another. You cannot reconstruct the entirety of the cosmos through observation alone. Some aspects of reality are permanently hidden from you, not because of opacity, but because of the structure of space-time itself. Furthermore, the horizon emphasizes the incompleteness of knowledge derived from observation. You may catalog all accessible galaxies and trace their evolution accurately. Yet the vast number of systems beyond your causal reach continues independently. Any model of the universe must accept that no observer can incorporate those regions into their empirical account. Observation is fundamentally limited, not by technique, but by expansion. In essence, the cosmological horizon is a reminder that causality is conditional. Unlike black holes, which isolate matter locally, the universe can isolate information on the largest possible scale. Past light can reach you. Future light cannot. The universe enforces a one-way connection. History is visible. Evolution is invisible. The horizon is absolute in its reach, quiet in its operation, and unavoidable in consequence. The accelerating expansion of the universe is therefore not just a dynamic phenomenon. It is a cosmic limit. It defines the boundary of influence, the separation of existence from relevance, and the ultimate incompleteness of any observational account. Reality continues beyond it, but your access to that reality is permanently curtailed. A finite observable reality. You live inside a bubble defined not by matter but by causality. Beyond it, events continue to occur without ever becoming part of your observable history. This means the universe can be infinite while your accessible portion is permanently finite. Completeness becomes impossible by definition. In your everyday experience, boundaries are easy to grasp. Walls, horizons, and barriers separate what you can interact with from what you cannot. Typically, limits are local and tangible. Travel, communication, or measurement can eventually overcome them. The bubble defined by causality is fundamentally different. It is not a physical barrier, but a structural constraint imposed by the geometry of space-time. The universe beyond your causal reach is not inaccessible due to distance alone. It is permanently disconnected from the network of influence and observation that defines your experience. The evidence for this bubble comes from measurements of the universe's expansion. Galaxies recede from one another at velocities proportional to distance, and this recession is accelerating. Beyond a certain critical distance, the rate of expansion exceeds the speed at which light, or any signal, can bridge the gap. Photons emitted now from those regions will never reach you. The light you observe today represents their past, not their continuing evolution. Their future is causally erased from your bubble, even though it unfolds according to the same physical laws as the regions you can access. This leads to a profound distinction between existence and accessibility. Matter, energy, and structure continue to evolve outside your causal bubble, yet they cannot interact with or influence anything within it. In practical terms, you can never obtain new information about these regions. Observation ceases to be a tool for extension. The universe may be infinite, but your portion of it, the segment you can ever measure or be affected by, is finite and bounded by a horizon defined entirely by causal limits. Time itself behaves differently in this context. Within your bubble, the passage of time is linked to observation. Events arrive as signals, and you update your understanding of the cosmos accordingly. Outside the bubble, time progresses, but those events have no way of entering your record. The unfolding of history continues independently of your capacity to observe it. The temporal flow remains intact locally, yet global continuity of influence is broken. Past light reaches you, future light does not. This structural finitude has implications for how you construct cosmological knowledge. All your measurements, models, and inferences are necessarily partial. You can map the observable universe, trace the formation of large-scale structures, and measure the cosmic microwave background, but you cannot assert knowledge of regions beyond the causal boundary. Any assumption of completeness is provisional and limited to what can intersect your causal past. Beyond that, reality persists, but it is forever outside the scope of verification. Even physical interactions are constrained by the bubble. Gravitational influence, radiation, and any propagating field are confined to your causal horizon. Masses beyond the boundary exert only what effects have already arrived within your domain. No new interactions emerge from outside. Influence and relevance become bounded by causality rather than proximity. Matter continues to exist outside, but its effects are removed from your universe of possible outcomes. The bubble also reframes the meaning of infinity in cosmology. The universe may be unbounded, with structures and events extending endlessly. Yet infinity does not translate to accessibility. You can experience only a finite segment, a finite set of histories and interactions. This decoupling of existence and observation forces a reconsideration of what it means to measure, to know, and to describe the universe in its entirety. Ultimately, the causal bubble is a limit imposed by the fundamental structure of space-time itself. It is not a technological obstacle, not a matter of insufficient telescopes or instruments. It is a permanent feature of reality, a horizon defined by what can never influence you, what can never become part of your observable history. Within it, the universe is coherent and measurable. Beyond it, reality continues, fully real yet inaccessible, ensuring that completeness in observation and understanding is not merely difficult, it is impossible. Measurement without completion cosmology measures the universe by sampling what reaches us. But horizons ensure that any dataset is incomplete in principle. No amount of patience extends your reach. The absence of information is not temporary. It is built into the structure of reality you inhabit. In conventional observation, limits are practical. Telescopes are finite. Signal strength declines with distance, Time imposes patience. In principle, improvements in technology or the passage of centuries could allow you to sample more, detect fainter signals, or integrate distant events. Horizons violate this assumption. They do not restrict you because of capability. They restrict you because certain events, no matter when or how, can never send signals that intersect your location. The limit is structural, not technological. Every dataset in cosmology is therefore necessarily provisional. When you measure the distribution of galaxies, the cosmic microwave background, or large-scale structure, you are capturing only a subset of the universe. The horizon defines that subset. Beyond it, events continue to unfold, yet they leave no trace in your measurements. Your models are constructed with an awareness that unseen regions exist, but those regions remain permanently inaccessible. Completeness is excluded by the very geometry of space-time. This structural incompleteness affects both space and time. Observations are a record of what has already emitted light, radiation, or gravitational influence toward you. Signals traveling from beyond your horizon never arrive, so their evolution is erased from your empirical account. You cannot observe future states of distant galaxies. Their ongoing transformations are entirely invisible, even though they proceed in strict adherence to physical law. The implications for inference are profound. Normally, you assume that uncertainty is reducible. Collect more data, extend your measurements, refine your models. Horizons make uncertainty permanent. Some events are causally forbidden from entering your knowledge. You can make probabilistic estimates about the regions just beyond your reach, but no calculation or observation can provide certainty. The universe guarantees that some truth will always lie beyond the scope of measurement. This limitation extends to the very concept of a global cosmology. You may speak of the universe as a unified entity, governed by uniform physical laws, expanding over time. Yet any empirical description is inherently local. What is true for the portion you can access may not represent events beyond your horizon, even if the underlying physics is identical. Observational completeness is unattainable, not because of imperfection, but because the universe enforces a permanent causal separation. Even the tools you use to bridge distance, light, gravitational waves, neutrinos, are subject to this restriction. Signals emitted from beyond the horizon today will never reach you. Historical signals that have already arrived provide only past snapshots. They cannot extend your reach into regions that are already causally disconnected. Patience or ingenuity cannot circumvent the horizon. The absence of information is baked into the fabric of space-time. This has profound consequences for interpretation. The limits imposed by horizons redefine what counts as accessible reality. What exists may be far larger than what you can measure. The universe is not fully knowable in principle. It is knowable only within a bubble determined by causal connection. Measurements are snapshots of a finite bounded domain, while the rest of reality continues independently. The horizon also reframes the role of prediction. You can extrapolate observed behavior to infer general patterns, but specific details beyond the horizon remain permanently unknown. Predictive models are constrained by access, not ignorance. The future of unreachable regions is not unpredictable in principle. It is physically disconnected from your observational domain. In this sense, cosmology becomes a study of partial knowledge. Every measurement, every dataset, every inference is limited by the horizon. Completeness is impossible, not because of error, chance, or insufficiency, but because the universe itself defines absolute boundaries of access. Measurement without completion is not an inconvenience. It is the rule, the consequence of the causal structure that shapes all observation. The horizon ensures that no matter how advanced your instruments, no matter how long you wait, some portions of reality will remain forever beyond reach. Your empirical universe is finite, while reality itself extends infinitely. Measurement proceeds, but completion is prohibited. Predictability ends at the boundary. Physical laws allow you to predict outcomes when initial conditions are known. Event horizons sever access to future initial conditions beyond them. This introduces a limit not just on observation, but on prediction. The universe remains lawful while becoming partially unpredictable. In ordinary experience, causality is reliable. Given sufficient information about a system, its position, velocity, composition, you can, in principle, predict its future within the limits of physical law. This principle underpins classical mechanics, thermodynamics, and even the statistical predictions of quantum mechanics. Observation and prediction are tightly coupled. The better you measure initial conditions, the more accurately you can forecast outcomes. Event horizons disrupt this coupling. When an object crosses a black hole horizon or a distant galaxy recedes beyond the cosmological horizon, the initial conditions governing its subsequent evolution become inaccessible. You may know its past, its mass, or its composition before crossing. You can model its trajectory until that point. Beyond the horizon, all future states unfold according to physical law, but you are causally excluded from observing them. Prediction ceases to be absolute. It is constrained by the limits of access imposed by the universe's geometry. This is not a failure of physics. Newton's equations, Maxwell's laws, and Einstein's field equations all continue to govern the dynamics beyond the horizon. Matter behaves normally. Energy is conserved locally. Entropy increases according to established rules. The universe remains lawful. The unpredictability arises not from randomness or breakdown, but from separation. The initial conditions required for prediction are permanently inaccessible. The deterministic fabric is intact, yet you cannot extend its implications into the causally disconnected region. The consequences for cosmology are significant. Any attempt to model the universe globally must account for the fact that future states of regions beyond your horizon cannot influence your observations. You can predict the observable evolution of nearby structures and radiation, but the evolution of distant, causally isolated regions is inherently unknowable. This introduces a form of lawful uncertainty. The rules operate consistently everywhere, yet knowledge of specific outcomes is limited by horizon-imposed boundaries. Even the methods of inference are constrained. You cannot rely on indirect signals to reconstruct future conditions outside your bubble. Gravitational influence propagates only within the causal domain. Photons, neutrinos, and gravitational waves emitted beyond the horizon today will never intersect your world line. The unfolding of events continues elsewhere, but you are disconnected from its consequences. Predictive models become projections, not certainties, once the initial conditions lie beyond causal reach. This tension between lawfulness and unpredictability reshapes how you think about determinism. A classical deterministic universe assumes that, given knowledge of initial conditions, all outcomes are knowable in principle. Horizons demonstrate that, in principle, is conditional on accessibility. Determinism exists locally. It does not extend globally from the perspective of a single observer. Reality remains structured, Yet some outcomes are permanently beyond your capacity to forecast. The effect also extends temporally. Even if you could watch the universe indefinitely, some regions would remain unpredictable from your perspective. Waiting does not restore access. Horizons define absolute boundaries in both space and time. The future beyond them is independent, lawful, and evolving, yet permanently removed from your predictive domain. This has implications for how science interprets completeness. No model, no data set, no theoretical framework can produce a full account of outcomes for all matter in the universe. Prediction, like observation, is bounded by causal structure. The universe enforces limitations not through randomness, but through geometry. Lawfulness is preserved. Accessibility is not. Ultimately, horizons demonstrate that law and knowledge are not synonymous. Physical laws continue, absolute and unbroken, but your ability to anticipate specific outcomes becomes conditional. The universe is orderly, yet partially unpredictable. Predictability is a local privilege, not a global guarantee. You inhabit a cosmos that obeys consistent rules while simultaneously defining regions whose futures will forever remain beyond your forecast. The paradox of causal closure. Within your horizon, physics appears self-consistent and closed, yet it is embedded in a larger reality that cannot interact with it. This raises a tension between local completeness and global incompleteness. Reality is consistent without being whole. In your daily experience, you expect that the laws governing a system define all that is necessary to predict and understand it. Objects behave according to known principles. Energy is conserved. Cause leads to effect. Within the observable universe, these assumptions hold. Local experiments, astronomical measurements, and theoretical models all converge to produce a coherent, reliable framework. Observed phenomena can be explained by physics operating entirely within the accessible region. Yet the apparent closure of physics inside your horizon is deceptive. Beyond the boundary, events continue independently. Matter collapses into stars, galaxies collide, supernovae explode, all without contributing any new information to your domain. The consistency you observe is preserved, but it is a fragment of a larger structure that remains forever inaccessible. Your horizon defines a self-contained causal system, but that system is embedded in a universe whose totality exceeds your reach. Completeness is local, global wholeness is absent. This distinction creates an unsettling paradox. The physics inside your horizon obeys all known laws perfectly. Predictions succeed. Observations align with expectations. Conservation laws hold. Yet the very notion of a complete universe loses meaning. You can never account for all matter or all events because the causal structure imposes absolute boundaries. The universe outside is lawful and structured, but its ongoing evolution lies beyond any empirical or theoretical closure available to you. The paradox extends to information and entropy. Within your horizon, you can measure energy distributions, map matter, and quantify entropy. Beyond the horizon, processes unfold without entering your records. Entropy increases in ways you cannot detect. Information continues to exist, but cannot influence your calculations. The system you can describe is complete in itself, yet incomplete relative to the broader universe. Local closure does not imply global completeness. Causal closure within the horizon also frames your conception of time. The future inside your domain is accessible to prediction, constrained by local laws and measurements. Outside, future states are causally disconnected. They evolve independently. yet their evolution obeys the same physical laws. From the perspective of your accessible universe, the rest of reality is neither random nor chaotic. It is simply unreachable. You cannot incorporate it into models, forecasts, or explanations, no matter how comprehensive your theories become. This separation is not a flaw in the laws of physics. It is a consequence of their structure in curved spacetime. Horizons emerge naturally from general relativity and from the metric expansion of the universe. They are not imposed arbitrarily. They are enforced geometrically. The self-consistency of physics is preserved locally, while global wholeness is impossible for any observer confined by a horizon. The tension between local closure and global incompleteness reshapes what it means to describe reality. You may construct perfect theories for the observable universe, accounting for every measurable phenomenon. These theories are valid, predictive, and exhaustive relative to your horizon. Yet by definition, they omit an uncountable number of events, structures, and evolutions outside your causal reach. The laws remain correct, but their domain is intrinsically bounded. This also alters the conceptual relationship between cause and effect. Within the horizon, causes produce effects as expected. Outside, the same laws operate, but the outcomes are invisible and irrelevant to your domain. The observable universe is self-contained in effect, yet isolated from the larger network of reality. Causality is complete locally, incomplete globally. Ultimately, the paradox of causal closure illustrates a profound limit to knowledge. Reality is lawful, consistent, and coherent where it can be measured, but it is fragmented where it cannot. Completeness is a relative property, restricted to causal bubbles, while the broader universe remains whole, yet forever beyond access. You inhabit a self-consistent portion of a universe that is always more than you can know. Entropy and hidden futures. Thermodynamics depends on counting possible states. Horizons hide states permanently. This changes how entropy is defined and measured. Black hole entropy is proportional not to volume, but to surface area, suggesting that hidden information still contributes to measurable quantities. In conventional systems, entropy quantifies the number of microstates compatible with a given macrostate. The more ways particles can be arranged, the higher the entropy. Observations of ordinary matter allow approximate counts of these configurations. Information is accessible, either directly or through statistical inference. Horizons disrupt this framework by introducing regions whose microstates cannot interact with the outside. These hidden states still exist, evolve, and obey physical law, yet their direct observation is impossible. The black hole provides the clearest illustration. As matter crosses its event horizon, the internal states continue to evolve according to local physics. Collisions occur, radiation propagates, structures interact. Locally, nothing fundamental changes. Yet the information contained in these states is causally disconnected from the outside. Standard entropy counting, based on accessible configurations, becomes inadequate. A new approach is required, one that incorporates hidden states into measurable quantities without violating the limits imposed by horizons. Remarkably, black hole thermodynamics shows that this is possible. The Bekenstein-Hawking formula assigns entropy proportional to the surface area of the horizon, not the volume of the interior. This implies that every bit of information that crosses the horizon contributes to a quantity measurable outside. The interior remains inaccessible, but its presence is encoded indirectly. Entropy becomes a bridge between observable and hidden realities, a measure that integrates causally isolated states into global accounting. This relationship has profound implications for understanding hidden futures. Regions beyond any observer's horizon evolve independently. Their microstates multiply, interact, and transform, yet contribute only indirectly to the observable universe. Entropy is therefore partially decoupled from direct observation. You can calculate total entropy in principle, but only as a function of horizon boundaries. The hidden information affects measurable quantities, but never reveals itself directly. Horizons also challenge conventional interpretations of the second law. Within a causal bubble, entropy increases as expected, but contributions from states beyond the horizon are permanently inaccessible. The apparent local rate of entropy growth may underrepresent the total universal rate. What you can measure is only a subset of reality. The second law remains valid locally, yet globally it must be interpreted with an understanding of hidden information. The universe evolves lawfully, but knowledge of its complete thermodynamic history is forever partial. This perspective forces a reconsideration of what information means in physics. Information is not synonymous with observability. A black hole demonstrates that states can exist, evolve, and contribute to measurable quantities without ever being directly accessible. Entropy becomes a proxy for hidden complexity, a tool to account for causally disconnected systems within the constraints of local measurement. Your understanding of reality must incorporate this distinction. What is measurable is not the same as what exists. The surface area scaling of black hole entropy also suggests a deeper principle. Physical law organizes hidden information in a way that preserves measurable consistency. Although microstates inside the horizon are inaccessible, they influence global quantities in a well-defined manner. Hidden futures are real, their complexity encoded in boundary measures. The interior evolves freely, yet its existence leaves a calculable imprint on the observable universe. Cosmological horizons extend this lesson. Just as black holes hide information inside their event horizons, the accelerating expansion of the universe hides the futures of distant galaxies. Their evolving microstates contribute nothing directly to local measurement, yet they exist and progress according to the same laws. The universe contains layers of reality whose complexity is hidden from any observer, but remains real. Entropy, in this context, becomes a tool for acknowledging the existence of hidden states while retaining consistency with measurable phenomena. Ultimately, horizons force you to confront the disjunction between existence and observation. Entropy is no longer a simple count of observable possibilities. It becomes a measure that accounts for hidden information, for futures permanently out of reach, and for the causal separation imposed by space-time itself. The universe is orderly, yet contains complexity that you can never witness directly, a complexity whose effects are felt only through the subtle, quantitative imprint it leaves on the horizons that define your observable domain. Surfaces that count more than interiors. The fact that a boundary can encode information about an interior challenges your spatial intuition. It implies that what happens inside a region may be fully described by what occurs on its horizon. Volume becomes secondary. Access defines relevance. In everyday experience, you assume that the interior of an object contains the information necessary to describe it. A box holds its contents. A room contains all objects within its walls. The interior seems primary, and the surface merely encloses it. Horizons force you to reconsider this hierarchy. For black holes, the Bekenstein-Hawking relationship shows that entropy, and by extension the total informational content of the interior, is proportional to the area of the event horizon. not the volume inside. The surface encodes what is otherwise inaccessible. This has consequences that ripple through both physics and philosophy. Inside a black hole, matter continues to evolve, particles interact, and structures collapse. Yet all of these states are causally disconnected from the outside. From the perspective of an external observer, the only meaningful measure of information is what is imprinted on the horizon. The complex interior is real, but its details become irrelevant to those outside. The surface is sufficient to describe the system as far as observation and thermodynamics are concerned. The same principle applies to cosmological horizons. Galaxies beyond your causal reach evolve and change, yet their internal dynamics contribute nothing directly to your observable universe. Any information that affects you is encoded at the boundary of causal accessibility. The interior dynamics matter only inasmuch as they influence what crosses the horizon. Volume exists, but its relevance is defined entirely by the capacity for causal connection. The surface becomes the domain of measurable reality. This inversion of intuition forces a reconsideration of how physical systems are defined. You may be tempted to equate size with significance. Large volumes contain more matter and energy, and therefore should contain more information. Horizons demonstrate that significance is a function of access, not scale. A region's interior may be vast and active, but if its states cannot influence your observations, their practical relevance is zero. What counts is the interface through which information flows. Surfaces that encode information also redefine entropy. Traditional thermodynamics counts microstates within a volume. Horizon-based entropy counts states that affect or are represented on the boundary. The interior may contain innumerable configurations, but for external measurement, those configurations collapse into a representation on the surface. This is the basis for the holographic principle, which suggests that a full description of a three-dimensional volume can, in principle, be stored on its two-dimensional boundary. Access is equivalent to reality. This principle undermines assumptions about locality. Information is no longer distributed uniformly throughout a region. It is concentrated at the horizon. The interior remains active, evolving, and lawful, yet its internal complexity is hidden. Observers measure only what is encoded on the boundary. Physical law preserves consistency without requiring knowledge of the inaccessible interior. The universe separates existence from influence, volume from significance, and interior states from measurable reality. The implications extend beyond black holes. Any system with a causal horizon follows this rule. The accelerating universe enforces horizons that function similarly. Galaxies, stars, and clusters evolve in regions beyond reach, yet the causal boundary determines what can impact observation or measurement. Surface area, not volume, defines the measurable content of reality. The universe teaches that relevance is determined by connectivity, not by extent. Even in principle, the interior cannot contribute additional information to an external description. Horizons encode all that is necessary for consistency with external physics. The interior exists fully, obeying the same laws as the exterior, but its states are effectively projected onto the surface. The interface, the horizon, becomes the locus of reality as far as an observer is concerned. Surfaces that count more than interiors challenge every assumption about containment, information, and observation. Volume is secondary. Access is primary. The laws of physics operate consistently inside, but relevance is defined by what can interact, what can be observed, and what can be represented on a boundary. In this way, the universe teaches that reality is structured not by what exists, but by what can communicate with you. Horizons make the invisible interior secondary and the accessible surface the defining measure of existence. The observer becomes central. Because horizons depend on position and motion, different observers have different accessible realities. There is no single, universal set of events that everyone can agree exists in practice. Reality becomes observer-dependent without becoming subjective. Segment 19. Time without shared futures. Two observers separated by sufficient distance may not share the same future, even if they share the same past. Horizons divide not only space, but timelines. The universe fragments into causally isolated histories that cannot reunite. Continuity. Without connectivity, space-time remains continuous across horizons. There are no breaks, tears, or discontinuities. Yet continuity does not guarantee connectivity. Smoothness coexists with absolute separation. Geometry replaces barriers. In everyday experience, continuity implies connection. A road stretching smoothly suggests that you can travel its length. A river flowing without interruption implies that one bank is reachable from the other. You expect that smoothness in space corresponds to accessibility. Horizons challenge this intuition. Space-time can be perfectly smooth, locally unremarkable, yet some regions remain permanently disconnected from one another. The absence of gaps does not imply the presence of pathways. This principle is evident at black hole event horizons. Locally, the structure of spacetime near the horizon is well behaved. A small measuring device would detect nothing unusual. The metric describing distances and intervals is continuous. Light moves at its usual speed. Physics operates normally. Yet globally, paths that once connected the interior and exterior are severed. A photon emitted just inside the horizon will never reach the outside universe, no matter how much time passes. The connection is broken, even though the continuum is intact. The same applies to cosmological horizons. Space between distant galaxies stretches smoothly. There are no physical obstructions in the intervening void. The geometry of space-time, however, expands in such a way that light from certain galaxies emitted today will never reach you. Continuity is preserved. There are no torn patches or missing regions. Connectivity fails because the metric itself dictates that the separation grows faster than signals can traverse. Smoothness coexists with permanent, causal separation. This distinction emphasizes a fundamental property of horizons. Separation is geometric rather than material. Barriers in ordinary life are objects that resist or deflect motion. Horizons are not objects. They do not push, pull, or collide. They exist as conditions imposed by the structure of space-time. The connectivity of events is determined not by surfaces or walls, but by the curvature and expansion of the universe itself. Continuity does not prevent isolation. Smooth space-time can enforce absolute boundaries. From the perspective of measurement, this has subtle consequences. Observables depend on causal interaction. You can detect radiation, gravitational waves, or particles only if they cross your light cone. Horizons prevent future interactions, yet do so without introducing anomalies in local measurements. Continuity guarantees that local physics behaves normally, but connectivity dictates what can be known or influenced. The observable universe is defined not by gaps, but by limits imposed through geometry. This separation also reframes the meaning of motion. You might assume that moving through continuous space allows access to any region given enough time. Horizons demonstrate that this assumption fails. The space is continuous, yet trajectories cannot bridge the causal divide. A smooth path exists mathematically, but it leads into an asymptotic future from which no signal or object can return. Continuity coexists with inaccessibility. Even causality behaves in this dual way. Cause and effect operate normally inside the local region. The laws of physics are continuous. Intervals remain finite, and time progresses steadily. Yet global influence is constrained. Events beyond the horizon do not participate in the local causal network. Smoothness of space-time allows processes to continue uninterrupted, but it cannot re-establish connectivity where geometry forbids it. Horizons also highlight the role of perspective. Different observers may assign different boundaries depending on their motion or location. Continuity is universal. The space-time manifold remains intact for all observers. Connectivity is relative, tied to what can causally affect a given observer. Geometry, not obstruction, determines interaction. Horizons enforce separation while leaving the continuum unbroken. Ultimately, continuity without connectivity forces a reconsideration of space itself. Space-time is smooth and lawful, yet separations can be absolute. Paths exist mathematically, but influence and observation are limited. The universe can be perfectly continuous while still partitioned by causal boundaries. Geometry replaces barriers, and smoothness coexists with permanent isolation. Horizons demonstrate that connection is not implied by continuity, and that the fabric of reality can remain unbroken while segregating events, regions, and information beyond reach. The silence beyond the horizon. You will never receive confirmation of events beyond your horizon. Their silence is not evidence of absence. It is enforced ignorance. The universe does not go quiet because nothing happens. It goes quiet because signals cannot arrive. In daily experience, silence often signals emptiness or inactivity. A room with no sound implies no movement. A street with no cars suggests absence of traffic. You naturally associate observation with reality. If you cannot detect it, it may not exist. Horizons expose the limits of this intuition. Regions beyond your causal boundary continue to evolve, yet their activity is inaccessible. Their silence in your observation does not indicate non-existence. It is a structural consequence of space-time geometry, an enforced inaccessibility rather than a lack of events. Black holes illustrate this starkly. Once matter crosses the event horizon, its ongoing interactions, collisions, orbital motion, radiation exchanges, become permanently hidden from external observers. Local physics inside the horizon proceeds without interruption. Matter continues to follow deterministic laws. Entropy evolves. Microstates multiply. Yet no signal from these processes can escape. From the outside, these events never occur in any empirical sense. Observation is permanently truncated by geometry, not by failure of physics. The interior remains fully active, yet silent. The cosmological horizon operates on a larger scale, but with the same principle. Galaxies receding beyond the horizon continue forming stars, experiencing supernovae, merging, and evolving internally. Their future emissions will never reach your instruments. The universe beyond your horizon is vibrant and dynamic, yet it registers as absolute silence to you. Observation is bounded by causal reach. The apparent quiet is not a reflection of inactivity, but a manifestation of the limits imposed by the expanding metric of space. This enforced silence affects how you interpret the universe. The absence of direct signals must not be conflated with absence of reality. Horizons make it clear that observable activity is always conditional. What you perceive is a subset of what exists. The universe continues beyond your reach in lawful, structured ways that you cannot detect, measure, or incorporate into empirical accounts. You can model the observed portion with precision, but no observation will ever extend to those silent regions. Even the concept of time is implicated. For events inside or beyond a horizon, time continues to unfold. Processes evolve, states change, systems interact. Yet from your vantage point, those events are frozen in causal isolation. You can never witness their progression. The silence is permanent. It is not a temporary delay awaiting signal arrival. It is the product of absolute separation enforced by space-time. Past light may reach you from before the horizon, but future developments are permanently muted. This principle redefines the meaning of measurement and evidence. In regions accessible to observation, causality and signals are sufficient to construct consistent histories. Beyond the horizon, histories continue, but their consequences are invisible. Knowledge is limited not by error, inaccuracy, or technological insufficiency, but by the geometry of the universe itself. Signals that could confirm ongoing events are forbidden by spacetime. Observation and reality are partially decoupled. Horizons also impose a conceptual asymmetry. You can catalog past events that have crossed into your light cone, yet the universe beyond the boundary evolves independently. Its silence is structural, and it is absolute. The activity of galaxies, black holes, and quantum processes continues unobserved. Yet these events are just as real as those within reach. Reality extends beyond perception, and the universe's ongoing vibrancy is permanently inaccessible to you. Ultimately, the silence beyond the horizon is not emptiness. It is enforced ignorance. The universe does not pause or diminish outside your causal bubble. It continues in full complexity, obeying the same physical laws, yet permanently beyond your ability to confirm or influence. Observation meets a limit, signals are blocked, causality ends at the boundary. The silence you experience is absolute, and it is a reflection of the structure of spacetime itself, not of the absence of events. Reality continues, fully real, quietly, beyond reach. Reality without witness events can occur without ever being observed, recorded, or inferred. This does not make them unreal. It makes observation optional rather than fundamental. Reality becomes larger than any possible account of it. In everyday experience, you equate existence with perception. You assume that what cannot be seen, heard, or measured is either absent or irrelevant. A fallen object in another room remains real only because it can be discovered. Your intuition links observation to reality, assuming that the universe is fully knowable through careful measurement. Horizons and causal limits expose the flaw in this assumption. Events can unfold entirely beyond your causal reach. They obey the same physical laws as observable events. They possess structure, history, and complexity, yet they leave no imprint on your knowledge. Observation is optional, not essential. Black holes demonstrate this principle vividly. Matter falling past an event horizon continues to interact, orbit, and collide. Quantum states evolve. Particles scatter, combine, and decay according to standard physics. Yet from the perspective of an external observer, these events are never recorded. The internal dynamics proceed independently, inaccessible in principle. They are as real as anything you can measure, but their reality is uncoupled from observation. The interior exists fully without witness, challenging the notion that reality requires measurement to be real. Cosmological horizons extend the lesson to the universe at large. galaxies receding faster than the expansion of space can carry their light, will continue forming stars, colliding and generating complex structures. Their evolution is causally disconnected from your location. No signal from these processes will ever reach your instruments. Entire histories unfold without being inferred, without being recorded, without leaving any trace in your observable universe. Reality continues beyond your reach, independent of measurement, unaffected by the absence of witnesses. This perspective reframes what it means to measure and to know. Measurement does not create reality, it samples it. Observation provides information about the accessible portion of the universe, but does not determine its existence. The universe is larger than any possible account. You can describe and model the portions within your causal bubble, but outside it, reality evolves fully, yet without connection to your empirical record. The completeness of your knowledge is always provisional, a subset of a far larger ongoing structure. Even the most fundamental physical laws continue to operate in unobserved regions. Quantum processes, thermodynamic evolution, and relativistic interactions unfold according to established rules. The lack of observation does not introduce inconsistency, error, or deviation. Reality is lawful, structured, and dynamic, even where no record exists. Horizons reveal that the universe contains layers of activity entirely decoupled from observation, yet fully real in the same sense as regions that can be measured. This separation also challenges conventional philosophical assumptions. You may assume that what is real must be knowable or measurable. Horizons demonstrate that reality does not require witness to persist. Events are autonomous from observation. Causally disconnected regions evolve independently, and their histories are complete despite the impossibility of recording them. Observation is optional. It is a tool for understanding, not a condition of existence. The principle has subtle implications for cosmology. Any description of the universe is inherently incomplete, not because of lack of skill, instruments, or technique, but because the universe is causally partitioned. Your account can never encompass all events, all evolution, all outcomes. Entire regions exist and evolve fully outside of your reach. Reality extends beyond your measurements, your instruments, your calculations, and your models. Ultimately, the universe is larger than any witness. Existence does not require observation. The laws of physics operate consistently, yet in regions beyond horizons, those laws unfold without leaving traces in your knowledge. Reality proceeds independently of verification. Observation describes, it does not define. The unseen, unmeasured, and inaccessible continues in full complexity, reminding you that the scope of existence surpasses the limits of any possible account. The universe is real, even where it cannot be known, and it proceeds without your witness. The limits of explanation. You can describe how horizons form and how they behave. What you cannot do is integrate their consequences into a single, unified picture of reality without remainder. Explanation functions locally while failing globally. In the familiar world, explanations are tools for connecting cause and effect. You observe phenomena, infer relationships, and construct coherent models. These models are expected to apply universally, capturing all instances of a phenomenon. Horizons, however, reveal a fundamental limit to this process. You can explain the formation of an event horizon in a black hole, derive its radius from mass, or compute its surface area and associated entropy. You can describe the acceleration of the universe and predict which galaxies will recede beyond the cosmological horizon. Yet these explanations do not produce a global picture in which all events, all states, and all causal consequences are fully integrated. There is always a remainder, an inaccessible segment of reality that escapes unification. Horizons enforce this limitation by decoupling regions of space-time. Inside a black hole, events continue, structures evolve, and physical laws operate as usual, but external observers cannot access this information. The interior is causally disconnected, meaning no global explanation can account for its precise states. Similarly, beyond the cosmological horizon, distant galaxies follow predictable local physics, but their future evolution is forever removed from your observations. No matter how comprehensive your models, you cannot incorporate these regions fully into a single explanatory framework. Local understanding is complete. Global understanding is inherently incomplete. This produces a subtle tension between lawfulness and comprehensibility. Physical laws remain valid throughout the universe. General relativity governs the curvature of spacetime. Quantum mechanics describes particle interactions. Thermodynamic principles apply locally and globally. Yet the presence of horizons ensures that the causal consequences of these laws cannot be fully traced by any one observer. The universe is lawful, yet no explanation can be universally encompassing. The completeness of reasoning is constrained by the causal structure of spacetime itself. Even measurement and observation cannot resolve this gap. You can measure all accessible light, gravitational waves, and cosmic radiation. You can map the observable universe with increasing precision. You can predict future evolution within your causal bubble. But horizons impose hard boundaries beyond which observation, influence, and integration into models are impossible. Explanation becomes a tool that works locally and fails globally. It captures parts of reality, but never its entirety. This limit extends to thought experiments and theoretical physics. Hypothetical extensions into regions beyond your horizon may be internally consistent. Yet they cannot be empirically validated. You can model possibilities, apply known laws, and generate predictions, but the inability to integrate actual states beyond horizons prevents a fully unified picture. Reality, in its entirety, remains partially veiled. Explanation functions as a local bridge over causal gaps, but cannot span them entirely. Horizons also challenge assumptions about completeness in cosmology. The universe may be infinite, yet your empirical access is finite. Any description you construct accounts only for the portion of reality within reach. Beyond the horizon, matter evolves, galaxies merge, stars explode, and quantum processes unfold, all independently of your models. Explanation remains partial, a coherent framework for a segment of the universe, but never an account of the whole. Ultimately, horizons demonstrate that explanation is necessarily conditional. You can understand formation, behavior, and local consequences. You can describe dynamics, compute outcomes, and predict accessible futures. Yet integration into a global, all-encompassing picture is prohibited. The universe permits local comprehension, but resists totalization. Explanation is real and effective where causal access exists, yet it fails where separation is enforced. Law, measurement, and prediction remain intact locally, but a fully unified description of reality without remainder is impossible. Horizons ensure that understanding always carries a limit, a boundary, and a portion of reality that must remain unaccounted for. Acceptance, without resolution. Physics accepts the existence of event horizons because rejecting them contradicts observation. Yet accepting them introduces unresolved tensions between information, causality, and time. These tensions are not anomalies. They are stable features of current understanding. You may assume that once a phenomenon is incorporated into physics, the conceptual framework resolves all its implications. Horizons defy this assumption. Black holes, cosmological boundaries, and regions beyond causal contact are real, measurable, and necessary for consistency with observations. Their existence explains gravitational lensing, orbital dynamics, cosmic expansion, and even the thermal properties of black holes. Observation compels acceptance, yet understanding the consequences remains incomplete. Tensions emerge between what exists, what can be known, and how information flows through space-time. These are not temporary gaps in theory. They are embedded in the structure of reality. Information illustrates the first tension. Local physical laws operate normally as matter crosses an event horizon. Particles collide, energy is conserved, and states evolve. Yet this information cannot escape. From the perspective of the external universe, the details are permanently hidden. Black hole entropy captures this discrepancy, encoding inaccessible information on the surface rather than in the volume. You can account for its statistical effects, but the fate of individual microstates remains unresolved. Accepting horizons means accepting that information can exist without being causally connected, a stable, unresolved feature of reality. Causality produces a second tension. Within a horizon, cause and effect function normally. Outside, paths that once connected events are severed. Signals cannot traverse the boundary, and future interactions are blocked. This preserves local consistency while violating the intuitive expectation that every event can influence all connected regions. Physics reconciles this by treating horizons as geometric constraints. Continuity remains, but connectivity is restricted. Local cause is complete. Global cause is forever partial. Accepting horizons entails acknowledging that the causal web of the universe is fragmented in ways that cannot be resolved by observation or theory. Time introduces a third unresolved tension. Outside a black hole, temporal progression behaves normally, allowing prediction and measurement. Inside, time points inexorably toward the singularity. The familiar distinction between past, present, and future collapses. For cosmological horizons, the observable future of distant galaxies is erased from your experience. The universe continues beyond your reach, evolving independently of your measurement. Accepting horizons forces you to accept that time, though continuous, is experienced differently depending on causal boundaries. The arrow of time is locally coherent, yet globally partitioned. These tensions cannot be eliminated without contradicting evidence. Observational astronomy confirms black holes through orbital dynamics, gravitational waves, and direct imaging of shadows. The accelerated expansion of the universe confirms the presence of a cosmological horizon. Every measurement that constrains mass, motion, or light propagation reinforces the reality of event horizons. Attempting to resolve the tensions by denying horizons leads to inconsistencies with well-established observations. The paradoxes are stable features, not optional puzzles. Acceptance without resolution reshapes the role of physics. The goal is no longer to produce a fully unified, all-encompassing explanation. Instead, it is to understand phenomena locally, model their interactions, and account for measurable consequences while recognizing that some aspects, information beyond the horizon, causal disconnections, future evolution of inaccessible regions, remain permanently unresolved. Physics succeeds not by providing total resolution, but by incorporating these boundaries into a coherent framework that respects observation, law, and consistency. Horizons exemplify the universe's capacity to be lawful and intelligible while simultaneously resisting total comprehension. They impose limits on knowledge, measurement, and prediction. Yet they do not undermine the predictive power of physical law where access exists. Accepting them is necessary, but acceptance does not produce closure. Information may exist beyond reach, causality may be fractured, and time may proceed differently across boundaries. These tensions persist. They are not defects. They are intrinsic features of reality as revealed by observation and theory. Ultimately, horizons teach that understanding does not require resolution. You can model, measure, and predict where observation is possible, yet the broader universe remains only partially integrated into any coherent narrative. Acceptance without resolution is the stable posture required by physics, a recognition that reality is orderly and lawful, yet fundamentally partitioned, with permanent gaps in causal, informational, and temporal completeness. The universe is consistent, but completeness is forever deferred. A boundary that is already here. You do not need to approach a black hole to be limited by an event horizon. You already are. Your observable universe is bounded by one, quietly separating what you can know from what will never enter your experience. This boundary does not announce itself. It simply defines the shape of everything you will ever observe. In your everyday life, the notion of a boundary feels intuitive only when it is tangible: a wall, a fence, or the horizon of the land. You naturally associate boundaries with obstruction or contact. Event horizons, by contrast, are invisible and pervasive. They are not surfaces that can be touched or crossed in ordinary terms. Instead, they are the causal limits of your universe, defined by the interplay of light, time, and the expansion of space. Every photon that reaches you, every gravitational wave that propagates to your instruments has already passed within this boundary. Beyond it, reality continues, but any signal it produces is permanently excluded from your observation. The cosmological horizon illustrates this most clearly. The universe expands, and space between distant galaxies stretches faster than light can traverse it. Galaxies that were once visible may recede to the point where their future emissions can no longer reach you. Signals from regions beyond this limit are blocked not by matter, but by the geometry of space-time itself. You live entirely within this bubble, a sphere of causally connected events, while the rest of the universe evolves independently. Your observable universe is finite, even if the total cosmos is infinite. The boundary exists silently, shaping all experience and measurement. This boundary affects every aspect of observation and inference. Measurements of light, gravitational waves, and cosmic microwave background radiation are confined to the interior of your causal bubble. Even the most sensitive instruments cannot extend the reach of observation beyond the horizon. Knowledge, prediction, and understanding are constrained not by the limitations of technology or patience, but by the fundamental structure of space-time. There is a hard limit to what you can ever know. What lies beyond is real, yet permanently inaccessible. The horizon also enforces a separation between existence and influence. Matter, energy, and processes beyond your observable universe evolve fully and lawfully, yet they leave no imprint on your local domain. They may produce structures, generate entropy, and obey the laws of physics, but none of this can affect you. The universe within your causal bubble is self-consistent and complete for the purposes of local physics, but it is embedded within a larger reality that cannot be integrated into any observation or model. Time, as you experience it, is also shaped by this boundary. Events within your horizon have causal chains that you can trace and, in principle, predict. Events beyond it unfold independently, and their futures are erased from the perspective of your measurement. Past light from distant galaxies may reach you, but future emissions are blocked. Your experience of temporal progression is confined, structured, and finite. The horizon defines the edge of the knowable timeline. This hidden boundary carries implications for the philosophy of observation. You are never fully at the center of the universe, yet your observational sphere defines a domain in which all experience, measurement, and understanding occurs. The cosmos is larger than your access, yet its larger reality does not affect the coherence of local physics. The horizon silently asserts its presence by delineating the reach of causality, influence, and knowledge. Ultimately, the boundary that defines your observable universe is already here. It is not an abstract limit or a distant feature to be approached in thought experiments. It is the framework that shapes every measurement, every prediction, and every perception. It enforces a partition between what can enter your experience and what cannot. Reality continues beyond it in full complexity, yet all that is ever accessible to you lies within its invisible circumference. The horizon does not warn. It does not obstruct. It simply is, quietly constraining what the universe allows you to know and leaving the rest in permanent silence.